Good afternoon. Whoa, that's loud. I am Bryna Kra, and I'm president of the American Mathematical Society, and I'm delighted to welcome you to the Colloquium Lectures. So, the Colloquium Lectures are our oldest series of lectures for the AMS. The first meeting of the AMS was held in 1895, the second in 1896, and that is when the first Colloquium Lectures happened. So it actually was at Northwestern University, my home institution, so I particularly have to point that out. This list of speakers who's given the Colloquium Lectures is a veritable who's who in mathematics. It includes Birkhoff, Morse, von Neumann, Tarski, Chern, Milner, Smale, Nirenberg, Tate, Stein, Tau. I mean, I could keep going on, but I won't list all of them for you. So it's my pleasure that I get to introduce Svetlana Jitomirskaya for this series of lectures. And she has won, again, a long list of prizes that I won't list them all, but she's been elected to the American Academy of Arts and Sciences. She's a member of the National Academy of Sciences. She's been an invited speaker at the International Congress of Mathematicians twice, the first time for a sectional talk and the second time for a plenary talk. She also serves the profession in numerous ways and is currently an elected member at large of the Council of the American Mathematical Society. So I won't keep you any longer from the mathematics, and it's my pleasure to introduce Svetlana, who will talk to us about quantum mechanics meets arithmetics and the Ten Martini Problem. Welcome.
Okay, thank you very much, Bryna, for the very kind introduction, and it's a distinct honor indeed to be speaking at this audience. And in general, these meetings are so inspirational because, you know, there are 6,000 participants and so different in different ways, and come here to celebrate what we all have in common. And what do we all have in common? So one thing is, please raise your hand if you have studied the number 2025 around the new year. Not everyone? Okay, less than I thought, but okay. Well, okay, so 2025, I would like to assume, maybe I'm wrong actually, that we all like to play with numbers. So let's look at the number 2025. It has many different interesting representations. Well, if you check, I like this one in particular. But which one is the most important one? Well, let us ask ChatGPT, because this is the theme of this JMM is AI and math, so let us incorporate, let's ask ChatGPT, what is the most important property of the number 2025? And indeed, it says that the most important property is that it is a square, 45 square, which is, yeah, it's a remarkable property. And indeed, so let us see, this is the square, the 45th square. And for many of us, it's probably the only year with such a property, right? Because the previous one was in 1936. Probably not many people in this room have experienced it. And the next one will be in 2116, and I hope some people in this room will experience it, but probably the majority will not. So for the majority of people in this room, this 45th, this 2025 is a unique square year. So let's take full advantage of it, enjoy it fully. Now, let's look at the triangular numbers. So everyone knows what triangular numbers are, right? So have we seen a triangular year recently? Anyone knows? Yes, we did. 2016 was a triangular year. And the one before that was 1953. So I assume there are some people in this audience who have already seen 2 triangular years. And the next one will be 2080. And again, I hope the majority of people in this audience will see 2 triangular years, 2016, everyone saw that, I hope, and the 2080. But some people will, like me, will sadly only have 1 triangular year in their lifetime. And I didn't even realize it at the time. I didn't enjoy it that much. I don't even know. So kind of, you see, there is this difference. Square years are a little more rare than triangular years. Some people do enjoy 2 square years in their lifetime, but most people do not. It's kind of the opposite for triangular years. So let us study it in more detail. So let us list square numbers in order. Okay. And now let's list triangular numbers in order. Fine. And now let us ask ourselves a question. How many triangular numbers are there between the successive squares? So let's see. Between 1 and 4, there are 2, 1 and 3. We always count the left one, but not the right one. That's our convention. Now, between 4 and 9, there is 1, 6. Between 9 and 16, there are 2 again, 10 and 15. And so we form this sequence of the number of triangular numbers between the successive squares. Now, it's not difficult at all to see, homework, that there cannot be 3 1s in a row. And there cannot be 2 2s in a row. So therefore, this sequence can be split this way into groups of 2 1 and 2 1 1, like this. Okay. Good. So now let us see how many 2 1s between the successive 2 1 1s. So you see it starts with 2. Oops. It starts with 2, then it goes 1, then it goes 2 again, 1, 1, and you can continue. And I don't have enough listed for you to verify that, but trust me, you get the same sequence all over again. So you can now repeat the process, and guess what? It will be the same sequence. And you can do it infinitely many times. So you have this interesting pattern that shows this remarkable self-similarities. It has bigger and bigger scales where the structure is exactly the same as at the lower scales, and it repeats itself ad infinitum. And this is the introduction to my talk. And pretty soon you'll see the connection, not immediately, to what I'm going to talk about. But so now bear with me for another introduction. So I'm going to talk about an exciting topic of quasi-periodic operators, something that where such patterns emerge naturally, and where there have been some great advances, mathematical advances recently, and which is strongly connected to physics, which is the title of my talk. Okay, so let us actually talk about connections to physics a little bit, the origin of these problems. So it starts with 2 colliding periodicities. So there are crystals, periodic structures, right? And so electron in a crystal is subject to a very, very regular motion. And a separate problem, electron in a magnetic field, also is a periodic motion. And what if you combine these two periodicities? And this is what was first done. So what results is the so-called tight binding model of, so speaking of two-dimensional crystals, of two-dimensional Bloch electrons in a perpendicular magnetic field. So this was first done. I'll explain in a second why this is the right operator, and I'll talk a little more about it. But this was first introduced by Peierls in 1933, so he specifically asked the question, what if these two, what will happen to the electron in such a situation? What are the properties of the model where these two periodicities that kind of don't talk to each other are combined? And he published a paper on that in 1933. And then he got distracted. He went on to work on some other projects. I guess some people know he was very active in the Manhattan Project. But then after the war, he decided to go back to important stuff. And so he looked at this problem again. And he gave it to his PhD student, Harper, to study further. And Harper published a paper in 1955, so more than 20 years after Peierls, which didn't go very far beyond the Peierls 1933 paper. But as a result, this is called the Harper's model. This illustrates to graduate students in the room how important it is to choose your advisor wisely. So you see, the model has really taken off in physics. Look how many hits in Google. See? You don't believe? Well, OK, you're right. It's not all the hits are relevant to this model. Right? But even if you do Harper model physics, still plenty, right? Again, not all are genuine, but still, it illustrates that it is extremely popular in physics. And so let us set it up mathematically, as I promised. So what describes electron in a pure two-dimensional crystal on the regular lattice? It's what we call a discrete Laplacian. Now, you can think if you are a PDE person, you probably have several problems with this. Why do I even call it a Laplacian? Because I do not subtract the center term, and I don't have a minus. It's all actually irrelevant in this discrete setting. It is a shift and unitary equivalent. So it's more convenient to deal with just this kind of graph Laplacian, right, adjacency matrix. You sum, so it's an operator that acts on L2 of Z2 and sends psi into the value at Mn as the sum over the nearest neighbors. Now, the more important question is whether this is a discretization of something continuum, or is it a model in its own right? So actually, it's a model in its own right. It is a so-called tight binding approximation, tight binding model. In physics, that's what Peierls actually dealt with. So it's a called tight binding model of an electron in a two-dimensional crystal. And then we can compute the spec. So this is a linear operator on L2 of Z2, and we can compute its spectrum. Now, OK, I probably should not assume that everyone knows what a spectrum of an operator is, should I? OK, I prepared a few slides explaining this. So, for operators acting on a finite dimensional space, of course, I need not explain it. It's just a collection of eigenvalues. Sadly, when you ask Google what is the spectrum, AI assistant tells you that the spectrum is a collection of discrete eigenvalues, even in quantum mechanics. This is emphatically not true, because in infinite dimensional space, this is, of course, a very problematic definition, because just take a basic example, operator on L2 of a measure space, operator of multiplication by a function f, right? So if measure your mu has no atoms, then, and f is, say, x on, suppose mu is on the real line, whatever, then this operator has no eigenvalues, right? And we want spectrum to be something that is non-trivial for any operator. So it's a bad definition. Now, luckily, this representation for matrices, this definition for matrices has also, as we teach our linear algebra students, has many other equivalent formulations. And it turns out that one of them actually is very nicely extendable to infinite dimensional setting. And it's precisely the set of E such that H minus E is not invertible. It's the same exactly statement in finite dimensional spaces, but it's more inclusive in infinite dimensional spaces because it can be not invertible, not just because it's not injective, but also because it's not surjective. And also it can not have a bounded inverse. So now, looking back at this example, the formal inverse of multiplication by f minus e, there is not much freedom. It must be multiplication by 1 over f minus e, nothing else. So therefore, the spectrum is a set of E for this operator such that this is a bounded operator. So such that this operator is well defined on the entire space and is a bounded operator. And so this becomes the so-called essential range of F. So the set of E such that for any positive epsilon, measure of x such that f of x is in E minus epsilon, E plus epsilon is positive. And spectrum is a unitary invariant. It's very easy to see. And in fact, the example that we just discussed is central because spectral theorem basically says that every self-adjoint operator is unitarily equivalent to some multiplication by a function. So going back to our discrete Laplacian, two-dimensional Laplacian, if you take Fourier transform in both variables, you see that immediately that it's unitarily equivalent to multiplication by 2 cosine x plus 2 cosine y on L2 of the two-dimensional torus. And therefore, its spectrum is the essential range of this function, 2 cosine x plus 2 cosine y, which is minus 4, 4. So we know what the spectrum is. Now, so that was, again, crystal, one periodicity. Now let's add another periodicity, add a magnetic field. So what does it mean to add a magnetic field? So basically, you need to weight your Laplacian by some phase factors, and phase factors are organized in such a way that so you incorporate this weights e to the 2 pi I a and e to mn here for these edges and for e to the 2 pi I b mn for vertical edges in such a way that when you go around each unit cell, you incorporate the 2 pi alpha for this ace if you go around in counterclockwise direction. So this is a model of magnetic fields. There are many different ways to do it. And So one way would be to assign 2 pi m alpha to vertical edges. So this depends on m, and just 0 to horizontal. This is so-called Landau gauge. It's an analog of the gauge that is used to solve the harmonic oscillator. And then your operator becomes like that. That's what I wrote in one of the first slides. I also include this parameter lambda here to reflect the possible anisotropy of the lattice when, say, jumps in the horizontal direction, or no, in this case, in vertical direction, are favored according to what lambda is compared to jumps in the horizontal direction. So this is my operator. And this represents this Harper model. This is the Harper model, tight binding model of two-dimensional Bloch electrons in magnetic fields. And again, as we just computed, if alpha is 0, if there is no magnetic field, the spectrum is the essential range. Oh, in this case, with lambda incorporated, it will be -2 lambda, 2 plus 2 lambda, but this entire interval. So the question is, what happens if you do include the magnetic field? What happens to the spectrum? And this is the answer. So this, let me explain what is plotted here. So on the vertical line, I have values of the flux alpha. So if alpha is 0 is here, which is the same as 1. This corresponds to alpha equal to 1/2, 1/3, and so forth. And on the horizontal, I have the spectrum of the corresponding operator with this flux. So this is a picture produced for 50 rational values of flux alpha. And so now, of course, especially young people in the room, you probably, especially if you attended math circles or something, you probably have dealt a lot with cutting off the Möbius bands and looking at fractals, right? So that's what everyone does nowadays from kindergarten on, right? But this picture was produced in 1976, and it was probably the very first fractal, beautiful fractal produced numerically. It was before the word fractal was coined by Mandelbrot. And it created quite a stir. So Hofstadter at the time was actually a PhD student, and it was not his first attempt at a PhD, actually. And in physics, his advisor was Greg Van Year. And originally, his advisor was very much against the idea that Hofstadter had that this can be something like this. So because you see what is nice here is that you have these little cells that reproduce distorted version of the large cells and so on ad infinitum. So you see this same self-similarity pattern like we saw at the beginning of the lecture in some sense. David Jennings described it as a picture of God. So I must say I recently gave this talk at a conference, not this talk, but a talk where I showed this picture and mentioned this as at a conference in Abu Dhabi. And there were some mathematicians from Saudi Arabia, and at that point, a couple of people got up and left the room. So I'm glad not to see this reaction here, because indeed, Hofstadter actually said in his book, Gödel, Escher, and Bach, that you may have seen, that he thinks this description is not blasphemous at all, because you see a structure that contains infinite copies of itself, and each smallest copy contains information about the entire structure. There is something about it. Anyway, so it is quite remarkable how this picture came about, because when this was kind of the first plot produced by Hofstadter. He was traveling at the time with his advisor in Germany, and again, year was 1976, and he didn't even have a computer with graphic interface, and he produced this picture by hand. And he realized, it seemed to him that there must be this self-similarity, which now that we have seen a better picture is clear to us, but looking at this picture, it may not have been. And then he, excited, brought it to his advisor, and his advisor told him that this is numerology, not physics. Stop it, and don't do such things. You will not get your PhD if you come up with such ideas. And the idea was that this is a structure that depends on continued fraction expansion of alpha, that this self-similarity depends on that. But the advisor, as we have seen, changed his mind upon seeing the better picture that was produced when they came back to Oregon. Another remarkable fact is that basically this same study was performed 7 years before Hofstadter's work in 1969. There is a published paper that has basically this picture, just one quadrant, this quadrant. And the authors and the readers, they didn't notice anything interesting. It was just a study of how spectra depend on alpha, and they didn't notice anything particularly interesting. But anyway, so this was this remarkable picture that brought Hofstadter immediate fame. And yet, it seemed like it was just a product of the mind. Yeah, okay, I forgot to say that why did Hofstadter notice it, and that's very important, because when he was a teenager, or before even his undergraduate studies, he really liked to play with numbers. And this example with squares and triangular numbers is something that he actually played with as a teenager, and he noticed these patterns that actually, maybe not that exact example, but something very similar. And the patterns also do depend. You probably don't recognize immediately why it is related. It is homework. Why is it exactly related, and why it is related to this certain continued fraction expansion. This pattern of squares and triangular numbers. But so he recognized it from his playing with numbers, and he recognized that there is this really remarkable thing happening in nature. But he thought that it is actually, even though he was a physicist, he actually quit physics after getting his PhD. He's in the Department of Computer Science now, but he said that he would be the most surprised person in the world if the butterfly came out in an experiment. That it is not something, it is just beautiful, but has nothing to do really with nature. And he said this in 1980. And in the same year, 1980, integer quantum Hall effect was discovered by von Klitzing. And the theory of Taulis is a Nobel Prize-winning physicist who worked at University of Washington, Seattle, by the way. It explains quantization of charge transport, and this effect is connected with Chern numbers, certain topological invariants, and central to the theory is the use of the Harper's model. So, and of course, this was just theory, but this was verified experimentally later on, and so this is I don't want to explain this picture, but this is certainly an illustration of Thouless theory of quantum Hall effect, by now an iconic picture produced by Yossi Avron. So here it is color-coded. Warm color correspond to positive Chern numbers, and cold colors correspond to negative Chern numbers. And this model somehow has this feature that it really keeps being related to new and new Nobel Prizes. So one's Fields Medal. And the interest has really was heated up with the discovery of graphene, because in graphene, you actually can, so the problem with experimental realization of this Hofstadter butterfly is that you need huge magnetic fields to see something. And in experiments with graphene, especially with bilayer graphene, you effectively get very large cells, and it's much easier to see these Hofstadter butterfly structures experimentally, and this has been all the rage in the last 15 years. So I'm just showing some pretty picture, trying to demonstrate how relevant it is. So again, let's go back to math. So this is our model, very simple. And that Landau gauge that I talked about, and this is a calculation that was performed already by Peierls in 1933. So you see, basically, this operator is periodic in one variable. So for those who know, you can just do Bloch-Floquet decomposition in this one variable, and this is sort of equivalent to what I'm saying. And this operator becomes unitarily equivalent to the direct integral in theta of such operators that are called almost Mathieu operators, each acting on its own fiber. So this means that the spectrum of this operator is equal to the spectrum of this operator. Here you see this theta is a dummy parameter, but the spectrum of this one becomes the union in theta of the spectra of these guys. But there is this very nice property that if alpha is irrational, the spectra of these guys do not depend on theta. This is a general property of ergodic, or more precisely, minimal operators of minimal dynamics. And therefore, the spectrum of this guy is exactly the same as the spectrum of this guy for every theta. And this guy has an advantage that it is a one-dimensional operator. We can involve one-dimensional methods to study it. So such these operators were called almost Mathieu operators. This name was introduced by Barry Simon. And so now I am ready to explain what is the Ten Martini problem. And the Ten Martini problem states something that is actually visually obvious from this Hofstadter butterfly picture. So you see these are spectra plotted for rational values of alpha. You see for each rational value, like 1/2, this is the spectrum. For 1/3, this is the spectrum, 3 intervals, 4 intervals. But if alpha is rational, something very nice, kind of Cantor-like, seems to be there in the limit. And that's precisely what the Ten Martini problem says. So this is actually well known that for rational alpha, the spectrum consists of finitely many intervals. But the statement is that for irrational alpha, there will be never any intervals. The spectrum will be a Cantor set, so perfect set with a perfect closed set with no interior and no isolated points. And it's with a structure determined by the continued fraction expansion of flux alpha. Remarkably, this was predicted back in 1964, before even any computation was possible, so not based on this picture by Mark Asbel. But people kind of didn't pay attention before Hofstadter's work. And in 1981, Barry Simon, he started studying vigorously these quasi-periodic operators, and he discussed Asbel's conjecture with Mark Katz, and Mark Katz offered 10 martinis for its proof. And that's it. That's why it's called the 10 Martini Problem. There is nothing more to it. So, but of course, what is important is that this problem was heavily advertised by Barry Simon. He put it in, he had a list of 15 problems in mathematical physics in 1985, problems that he deemed really important, like the stability of crystals and so forth. And there were several problems related to this almost mature operator, including this 10 Martini problem on this list. And then he doubled down in year 2000. So of course, this attracted people to this. And so this is a problem, that the spectrum of this operator is counter-set for all irrational alpha. And there were, many people have worked on it. There were some substantial partial solutions done by many authors. And there was a key breakthrough. I'll explain some of the progress a little later. There was a key breakthrough by Joachim Puig in 2004. And the final solution was given in our paper with Arthur Avila in 2006. So now it is 2025, so why am I talking about it now? Right. Okay, so, before that, let me just say that you hear this problem mentioned in the session on spectral theory of ergodic operators that we run on today, Thursday and Friday, with Nathaniel Levy and Matt Powell. You will also hear another talk on this problem by Dan Borgnia on Friday. And if that was not enough, Emily Lotkin will talk tomorrow in the Exploring Mathematics through the Arts and Pedagogy in Creative Settings. And look, this is an excerpt of her poem about 10 Martini. Right. So, but again, so why am I talking about this now? Because I spent all this time to show the relevance of this problem to physics with a purpose, because if a problem is actually relevant to physics, this statement should kind of be a little robust. So again, this 10 Martini, with all this beautiful history that was finally proved in 2006, was specifically for this family. So what if we change the cosine? Put another nice function here. Just something really, really close to the cosine. It should be kind of the same. Physically, putting something nice and really close to the cosine corresponds to just allowing the interactions not just with nearest neighbors, but decaying interactions with further neighbors, a very, very natural assumption. So what are the past results for, let's say, nice functions V other than lambda cosine? And the answer is none. So there have been no results like that, not a single other continuous V. So for this continuous V, there have been some nice results, but I don't have time to mention them. So that would prove this result, Cantor set for all irrational alpha. So let us talk about why. So there are two aspects of the proof of this Ten Martini for the cosine that made it difficult to extend. So one aspect of the proof, of all past proofs, was that even though the statement is that something holds for all irrationals, the proofs had all approached different irrationals differently. So in particular, one can loosely define Liouville alpha, the ones that are abnormally close to the rationals. There are measured theoretically few of them, but they form a dense G delta, so topologically rich set. And Diophantine alpha, this is a full set of full Lebesgue measure. And some proofs depended on this existence of a subsequence of rationals that approximate alpha very, very well. And some other proofs depended on the fact that alpha is sufficiently far from all the rationals, that alpha is Diophantine. So the proof from the Liouville side all based on algebraic argument of Choi, Elliott, and Yui, which is actually a remarkable argument, so-called non-commutative binomial theorem. So if you have a non-commutative ring like that, where gamma commutes with A and B, then this it's a neat fact in its own right, due to Choi, Elliott, and Yui, then the coefficient, let's denote it like that, in the expansion of the binomial in this ring is equal to the value at gamma of Gaussian polynomial. And they use this fact to show, so basically then for rational values of alpha, if alpha is m over n, then the spectrum is where a certain polynomial defined like that is less than 2, and this polynomial have coefficient defined through Gauss polynomial with gamma equals to 2e to the 2 pi I m over n, and they use this fact to bound from below the gaps for rational values of alpha. And once you can bound gaps from below for sufficiently Liouville alpha, you can establish also bounds on gap. You can show that the gaps are still there. So that is Choi, Elliott, Yui proof in a nutshell. And so this was a paper published in '91, which established Cantor spectrum for Liouville alpha. And then in 2003, Puig established Cantor spectrum for Diophantine alpha, using the statement about pure point spectrum for almost Mathieu operator with very specific values of theta, theta equal to 0, that was established in my paper a few years before that. And it is a very nice and very beautiful argument that this localization, which is a pretty difficult fact actually, that this implies, so again, I am talking to the experts now, but tomorrow what I'm saying here will become more clear. So this implies, reducibility at each eigenvalue to such a matrix, which, if C is not 0, implies that we are at the at an edge of an open gap, and since eigenvalues are dense, it would mean that open gaps are dense. And if C is 0, and C is 0 is impossible by simplicity of the eigenvalues of second difference operator. Again, it will come as a theme in what I'm going to talk about, so this particular last thing I want to emphasize. So note that after these two papers, the statement of Cantor spectrum was established for Liouville alpha and for Diophantine alpha. There was basically, so for Diophantine, this Puget's result established the statement for almost Cantor spectrum for almost every alpha. So what I thought after his work, I really kicked myself because it was kind of rather simple addition in some sense to the more difficult localization statement. But I thought that this was done. And then Arthur Avila came, he visited me in 2004, and he said that, okay, let us finish it. And I was very reluctant originally because I said that, okay, there is so few alphas left in the middle. It will be difficult, technical, nobody would pay attention. But apparently he was right and I was wrong, so it was very important to actually obtain an argument that works, that covers the entire range. But in our proof with Avila, we had to establish some different arguments in the Diophantine regime because these two approaches pushed to their technical limits could not quite meet in the middle. But in the Liouville side, so our Diophantine approach used some elements of Puget's argument, but also developed some very different things. But on the Liouville side, we still relied on the Choyolet and Yui. We just improved a little the approximation for which Liouville numbers it works. So basically, there were two approaches, still two different approaches that met in the middle. And we wrote in our paper that we see it as some sort of a miracle that they do meet in the middle and that we don't see good reasons why they should for other models. So I'm very tempted here, though, to reproduce a slide from my that I used when I gave talks about this some 20 years ago, about how these two approaches meet in the middle, and that for Diophantine fluxes, the proof uses chaos localization. For Liouville fluxes, it uses order, gaps of periodic approximants, and the arithmetically critical region in the middle requires a miraculous collaboration of both approaches. So, so again, let us go back to our question. My time is almost up, so today I at least have to formulate a theorem, and I'll hopefully tell some really neat ideas that go into its proof. So this is the reason. There is also another reason, I'll repeat it tomorrow, that other than that, each element actually requires cosine in many, many places. And particularly so, this algebraic argument of Choyolet and Yui. This is something. So if we, in the work that I will show, actually manage to extend some of these ideas to other functions, this one is still completely up for grabs. This does not, we don't know how it works for anything else. So, and the subject of my lectures actually is the robust Ten Martini problem. That's why I'm giving them now. And it is this theorem, joined with Ling Ruige and Jiangong Yu, that actually Ten Martini holds not just for the cosine, but for an open set of analytic functions V. And this set includes perturbations of the almost nature, that was what was desirable, but also perturbations of some other models that were popular in the literature. So, and I guess I'll leave the rest for tomorrow.